This is the Amp Hour Podcast, released April 3rd, 2022. Episode 584. Software for Rockets with Charles Aylward. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Charles Aylward of Grizzly Peak Systems.
Hey, Charles. How you doing?
I'm good. How are you doing?
I'm good. We know each other from the consulting forum, but also your name has come up a bunch in, like firmware kind of consulting things. And past guest Todd Bailey said he was working with you, I believe, at a new space company.
That's right. Yeah, we both worked at Astra together. That's actually how we met.
Oh, cool. Okay. So you met on the job. Yeah.
Mm-hmm.
And we have not caught up with Todd in a long time, but he's been doing lots of spacey type things in the meantime. So we were talking about this a little bit before the show, but what is new space? How do you define new space versus just space?
Right. Yeah. So, I mean, it's certainly not an official term of any kind, but people who work in new space, I think, probably sort of differentiate it from old space. So it's the difference between maybe like, say, if you're taking the extremes, like a 60s or 70s, or even just like 80s, like NASA approach, like kind of a top-down design, really using basically
waterfall method and subcontractor to subcontractor to subcontractor type of thing, or
yeah, I mean, maybe it has less to do with like how deep your contracting goes, but it definitely has to do with like basically like the specifications of the parts that you're willing to tolerate, right? So
interesting. Okay.
NASA is not going to take any chances, right, with anything, right? So I've never worked at NASA, but I presume they spend a lot of time in analysis, and I've certainly read some papers that lead me to believe they spend a lot of time with lots of really rigorous analysis, and they know for sure that their systems are going to work. And if you're sending something to Mars, right, that has to be the case.
It's got to be 1,000% tested. Yeah. And I always think about like rad hard parts. You see them on like a DigiKey or Mauser, and you're like, oh, why is that 20-year-old CPLD costs $3,000? And it's because it's rad radiation hardened or whatever, and they've done all this pre-testing on it and pre-characterization.
Right. It's like right. It's like 40 megahertz CPU, and it costs like $12,000 or something.
Yeah. Z80, it's the new hotness. Yeah.
So new space, to contrast, is sort of taking a slightly different approach. So in the case that you're not sending things to like Mars or even necessarily like the moon or something, you're just sending it to orbit, like generally low Earth orbit. The idea there is build smaller, cheaper things. And because they're smaller and cheaper, you can afford to send more of them. And because you can send more of these things, then you don't have to max out all the specs, because if 1 in 3 fail, maybe, or whatever it is you decide for your mission, 1 in 3 fail, maybe that's still fine.
Right. Yeah, and we've talked to people on the show before. So we've had Sean on from Planet Labs. We've had Joris on from Hyber. We've had, I forget the last one, but I think that was all on the payload side. So like things that were going up to space. You guys were working on the thing that was launching. Is that right?
Correct. Yeah. So we were working on the launch vehicle. And I mean, we could talk about like the thermal and radiation environment and all that a little bit too. Maybe in general, once you are in LEO, I mean, you have to care about these things, right? You have to care about radiation and the thermal environment. So whether it's a payload or the launch vehicle, you kind of need to care about the same amount.
Okay. And so this is a launch vehicle. I remember I only read a couple articles about Astra in general, but a much smaller rocket. Is that right? Like it's kind of like meant to launch small sats, or what is the nature of the launch vehicle?
I guess, yeah, you would just call it a smaller launch vehicle. So, they're like in the class of like a rocket lab vehicle. So these things kind of like all feed each other, right? So I think if we go back, Planet Labs, or now just Planet, sort of really proved this idea of using a little bit more like commercial software or commercial electronics, commercial level electronics instead of like rad hard systems. And then you can just fly a lot of these things. And so they sort of prove that, this sort of like lots of small systems kind of can compete with, a single big expensive system. But then there's still this problem of, well, how do you get it to orbit? Well, you have to like find some massive rocket and maybe try
Right.
to like it's either going
Hitch
to
a
be
ride,
really
basically.
it's going to be really expensive to send all of
Yeah.
your payloads, or you can maybe find a ride share. And then the
Yeah.
problem with finding a ride share where you're basically tagging along with some other major payload.
Surge pricing is it surge
Yeah.
pricing like
Yeah, I mean, you're kind of subject to whatever you can get in terms of the availability, but then also you have no control over when you're going to launch.
Yeah, right, right.
So it seemed, I think, obvious to quite a few people that there's a niche there. So
That's cool.
a rocket that is commensurate with small sats and CubeSats, commensurately sized.
Yeah, so kinda like shrunk down. Isn't there like I remember seeing a talk about the rocket equation. I have no knowledge of the rocket equation other than remembering I went to a talk about it, so I didn't pay attention very well. But isn't there like a size thing anyways, like where as you get bigger you need to carry more fuel? That's the main gist of what I remembered. Like so does that advantage a smaller rocket or does that disadvantage a smaller rocket?
It's an advantage. Yeah. So the main gist of like the limit on the rocket equation is that as you get a bigger launch vehicle, most of the weight you're carrying is fuel, right? So at
Yeah,
some
yeah.
point you reach this like law. There's like a diminishing return where eventually you're just basically spending all of your energy transporting fuel.
Mhm. Yeah.
And so if you're looking at like the ratio of the dry mass of the vehicle to like how much fuel you need to get it to certain orbit, right? You can kind of like graph these things and figure out how big a vehicle you need to get so much mass into orbit at a
Yeah.
certain orbit, and then you can kind of figure out how strong do the engines need to be, that sort of thing, and kind of flow down through the design that way.
Yeah.
If that makes sense.
Yeah, I mean, at least at a very very high level right now.
Right,
As
right,
you
yeah,
say it, I'm like, yeah, Charles makes a ton of sense right now, and this is, I think I'm a rocket scientist now.
yeah. Sometimes I haven't tried to actually explain it at any particular level, so it's kind of
Hmm, okay,
an exercise right now.
first pass, it was great. It was great. So, I mean, you were not designing the rocket part. You were designing the control piece, I believe.
Correct. Yeah. So I'm definitely not a mechanical engineer or a propulsion engineer, et cetera,
Yeah,
or
yeah,
fluidics engineer. So
yeah.
there was a team that is focusing on the propulsion system, so basically the actual engine design. And there's a structural team, working on tank design and basically how the engines get mounted and all that sort of thing. And I worked on the electronics and software, although originally actually it was mostly just software.
Hmm.
And there's a couple different classes of software on the vehicle. So, kind of broadly speaking, you would have sort of power management systems and then your sort of flight control systems or avionics systems.
Okay. One thing that I wanted to have as kind of like an overarching topic for this episode,
Mhm.
because Charles and I interact on the consulting forum as well, is one thing that I admire about him is the level of rigor that he puts toward that you, I'm talking to you, I suppose. I'm talking to the audience as well, but like the rigor that you kind of bring to your engineering practice. And I thought that actually plays really well in the big things go boom space, also known as rocket.
All
So
right. Yeah.
how does that all play together? I mean, like what is it? How the hell do you know that you're ready to hit the big red button and launch that thing into space from a software or hardware perspective?
Yeah. Well, of course they're pretty intimately related. So, right, yeah.
Yeah.
So yeah, I mean, just like starting from the main point you made there, right? You're talking about a lot, even a small launch vehicle. You're talking about a lot of energy. You don't want that to fall out of the sky in the wrong place, or right, just chaotically end up somewhere it's not supposed to.
Hmm.
And then even before you hit that big red button, when you're testing the vehicle, there's a lot of things you want to make sure do or do not happen. There's a lot of very strong actuators on there. You want to make sure, if a technician is in there changing or modifying something, something's not going to like suddenly move,
Rip their finger off. Yeah.
connect the power to something, and an actuator, right, tears your arm off or something.
Yeah.
These are
Yeah.
other things you don't want.
That's gonna ruin your coding efficiency for sure. Yeah.
Right. Yeah, I guess I could start at sort of like maybe a generalized process that I would run through for.
Sure. I mean, sure. I guess one thing is, I mean, how big is it? So you said new space, and I think startup, but like, how big is a team that's doing all this stuff? Like, how many people are you? Is it just you writing software? Or are the other people writing software? Like, how does it all interact? I guess at a very, very high level first.
So this is probably a unique experience generally, but there was a joke for a long time that I was the software team at Astra.
Oh wow. Okay. Yeah.
At least at least for the vehicle, for like the flight controls
Uh
software.
huh. Yeah.
I mean, there are other software engineers working on ground systems for sure.
Hmm.
For a good chunk of the first one or two launch vehicles, I was sort of the single flight control systems like software engineer, with one exception, which would be the actual guidance, navigation, and control algorithms. There's an engineer who focused on the the sort of control algorithms. So, let's say two engineers.
So then what do design reviews look like then? I mean, is it that's got to be kind of crazy. I mean, either you're checking your stuff so rigorously or setting up tests or whatever, but like, yeah, what does a design review look like then?
Yeah, that was quite a challenge early on, and until I mean, we later on, of course, we did build out the team a little bit, so could actually have a little bit more rigorous, design reviews. And even though you mentioned Todd Bailey, even though Todd Bailey was sort of focusing on electronics at the time, I mean, he knows firmware as well, and
Hmm.
we
Yeah.
bounced a lot of ideas off of each other, and he certainly helped review a lot of my work. So it wasn't totally me in terms of like testing and the sort of rigorous part, but in
Hmm.
terms of day to day typing code into a machine, it was definitely
Yeah,
mostly me.
that's a lean crew. I mean, that is a lean crew. That's impressive.
Yeah, it's certainly not advised. Like that was
Right, right.
that was it was one of these things where when I interviewed, it wasn't hidden from me that I was basically the only person at the time. And I think when I interviewed, the idea was go from basically zero to launching in 6 months. And I was like,
Wow.
you know,
Okay. I mean, that is an exciting proposition though. Like that is like,
it
oh, okay,
is.
yeah,
Yeah.
yeah,
And,
yeah.
and I did make the mistake thinking that, well, I know how stressful this is going to be going in and how, grueling that is going to be. And because I know that, that'll help. And it kind of turns out that doesn't help that much.
Yeah, there's still only 168 hours in the week, and you sleep
Right.
a little bit, I guess, and your code
Yeah.
goes down as your sleep goes down, and yeah, that sort of thing.
Right. Yeah.
So, is there a dev kit that I can buy that like where does one start then in the whole like, all right, we're gonna put something in space. It has to be controlled. There's no dev kit, I'm guessing.
No, there definitely is no dev kit. Although there's certainly a lot of like example kind of systems, and depending on how you decide to design these things, of course there's existing software you can kind of maybe build off of. You know, we can maybe get into it a little later, but like one of the things that's going to come up is like, well, you have real-time constraints. Do you use a, real-time operating system, or and which one do you use, that sort of thing.
Yeah.
kind of going back to like, well, if you have a really lean team, how do you structure things so that you can be reasonably sure what the system behavior is going to be? And I think one of the things that Todd and I worked on before we wrote a single line of code that was a really great idea was we kind of came up with a set of what we called, like, at the time we called them guiding principles. I've called them other things at other places, but guiding principles with regards to system architecture. So like sort of high level things.
Give us an example one, maybe.
Yeah, yeah. So the first thing you want to do is figure out what classes of problems you have, right? So in something like a launch vehicle, it's not feasible to just have like a single embedded like compute device with all of the sensors and all of the actuators plugged into like, a single CPU or processor, right?
Hmm. So no Arduinos.
You're right. So it's very likely that when you like think about these things, you're going to have like these natural sort of boundaries. Like, well, you're going to have electronics on a engine, and that engine should sort of know how to do engine things. And
uh,
right, you have a flight computer that knows how to do guidance and navigation things, and then you have
got it.
different controllers that maybe know how to like open and shut valves and read temperatures, that sort of things. So because you have these different systems, off the you sort of off the bat have minimally a distributed systems set of problems, right? Like, what does it mean to have a distributed system? The simplest way to put it would be you have slow or potentially lossy communication
Yeah.
channels between
Yeah.
systems, right? There's a couple different ways
best
you can.
best case is asynchronous, right?
Yeah,
Perfect asynchronous system.
there's a
Yeah.
couple different ways you can approach thinking about distributed systems. Another one would be like you have more than one clock on the system,
Mm. Yep.
right?
Yep.
So you have in the case of like a launch vehicle, you might have the flight computer has a clock because it needs to have very precise timing to do all of its guidance algorithms, navigation algorithms. But then engines also need to be able to very precisely synchronize things. So they might need their own clocks, right? So now you have like two clocks that you need to,
Hmm.
you know, deal with that problem.
Yeah.
But in general, anytime you have a system where communication between two things can either, like in terms of like, if you're talking about packets, you can miss a packet could be delayed, you could get two packets out of order, right? That sort of thing. Or you could get the same packet twice, perhaps, right? So you have to be able to anticipate those things. And then sort of going back to like, what classes of problems do you have? Well, the timing for starting and running a rocket engine is very precise. And sometimes there are very small amounts of time between, actions that need to occur. There can't be like a large variance in those timings because you're controlling valves and there are fluidic effects and that sort of thing. And so you can't like flood the engine, you can't starve the engine, that sort of thing, of just using very general terms, right? So
Yeah. Yeah.
you need to have precise timing. So you have, and then guidance and navigation also requires precise timing. So you have, you have real time classes of problems, right? You can't be late solving your navigation solution, right?
Ah, okay. So you're saying like you have hard deadlines you have to meet. In addition to lossy comms, you have to be able to synchronize and meet deadlines between different domains.
Right. Yeah, I mean, if something like if you're like talking about a car or a launch vehicle or whatever it is, of course, you from a physical standpoint, you want to assume that you don't have lossy comms. Let me rephrase that. From a physical standpoint, you want to design the system to not have lossy comms, but from a software perspective, you have to design around the fact that you might have lossy comms, right?
Yeah, so like acknowledgments and things like that are
Yeah,
ways to tell if you've delivered a message.
if nothing else, it's a very noisy environment, and you might actually just simply have bit errors on the line, right? So,
Oh, wow. Yeah.
right.
So then I think CRCs and other ways to validate that a message is legit.
Yeah, exactly. Yeah, so well, that does feed into like going back up to like this coming up with guiding principles for your software, actually not even necessarily for your software, but just for
Yeah.
like the behavior of the system, right? So from the highest level, really,
Hmm.
what you're trying to get is a system that's testable, right?
Yeah. Yep.
but also very importantly that like you can understand it, right? Like you can understand basically somewhat small enough that you could fit it in the human brain, right? So if you have two systems, you know what the behavior is going to be given any particular whatever command sequence, right? So you want, high levels of determinism in your system.
Oh, okay. So not like you don't mean like human readable, like it's not like sending JSON packets between two domains or something. You just mean that it's not overly complex?
Yeah, right. So I mean, maybe the best thing to do would just be get into a couple of these principles that I've thought about,
Sure. Yeah, that'd be great. Yeah. Yeah.
give you some examples, right? So the first one I start with usually is no modes. So your software doesn't have basically like fundamentally different operating modes. There's only the mission mode, right? So you don't have like a
Mm.
test mode, you don't have a debug mode, you don't have these different modes that you can put it in where the total system behavior can suddenly be radically different.
That is a great one. Oh my gosh.
Yeah, that sometimes even includes like things that seem like they would be a good idea, like safe modes, right?
Mhm. Yeah, because then the question is, well, why isn't everything in safe? Why isn't everything safe in some way, right? Or yeah.
Right. Like I can't remember the link exactly, but there's a gentleman who basically catalogs all of, basically like software failures on space systems. And a very large percentage of those failures are from a mode. Basically, the system decided something wasn't right and it put itself into a safe mode. Simultaneously, some other system put itself into a safe mode. And that second system was the thing that should have taken the first one out of safe mode. And then like
Ah.
the system is just like permanently saved, right? That's like the simple
Safe as in
example.
like inert.
Exactly. Yeah, there's some pretty famous, like, high profile systems that have failed for reasons like that.
Huh.
And so this kind of follows into, like, some of the other principles you might have, which is like, well, if you don't have modes and you don't have a test mode, well, how do you test it? One principle might be debug data and test data is first class data. There's no difference between test data and like mission data. And so like, well, what does that mean for like a software system? So basically means exposing in your telemetry, however you're getting that telemetry, basically synthetic sensor data, right? So
Hmm.
generally you already have like a bunch of sensor data and a bunch of commands going out to actuators. So you're already dealing with like sensor data. And I found it somewhat surprising. Some people tend to get hung up on it being like a physical sensor. And, there's no reason you can't just have a synthetic sensor data piggybacking in on this, sensor system you already designed. So, simple things like error counters and, a counter for like CRC failures and things like that, or counters for failed or like missed deadlines, average latency to read, some ADC somewhere way down the line, that kind of thing. You can just pipe all these things in with your sort of mission data, like temperatures and
Hmm.
actuator positions.
So, I guess how does this get treated in other systems that you were kind of not doing it the traditional way? I suppose.
Sorry.
Like, what does test data and debug data look like in systems that you were not designing?
Oh, well, I mean, I think just so like to really generalize it, I think it's just sort of approaching the software with the perspective that if something unexpected happens during testing, like from the behavior of the system, something unexpected happens during testing, do you need to like hook up a JTAG connector to figure out what's going on? Right.
Ah, I see. Okay, so it's about exposing interfaces and data so that it's kind of always available.
Yeah, it's exposing your internal state as much as possible, right?
I
In
see.
like some meaningful way.
I always kind of assumed that wasn't the case because there was maybe constrained channels. Like if so, using a very very simplistic example, if you have a UART running at like 115K, then like
Mhm.
you could only get so much data through that, and if you have to choose between mission data, which you're putting through a UART for some reason, or test and debug data, you would deprioritize the test and debug data. Is that a fair statement?
I'm not sure because you when you're doing the system design, you can kind of it's sort of, I think the way you put it presupposes that the electronics are just being dumped on you post hoc, and then you have to, like, figure out
Hmm.
how to get the
Yeah.
stuff fit in there.
Oh, well, yeah, actually, what I'm really asking is, I was wondering if you had to like kind of up spec communication mechanisms in order to fit a wider volume of traffic or larger volume of traffic as a result of this.
Yeah, that's true. So
Okay.
you would need to, like, you're definitely not talking about 115, 200K or 115, 200
Yeah. Yeah.
UART.
It's a bad
So,
idea to squeeze it all through that tiny pipe.
yeah. So, if you have a moderately fast CAN bus or if you're using Ethernet, right, chances are you've
Hmm.
got the bandwidth and, let's say, 10 or 20, synthetic, software sensors is probably not gonna kill your budget.
Yeah.
Yeah,
Got it.
or you can
Okay.
just approach it from the perspective of making sure you have that bandwidth so that you can include the software
Yep.
telemetry.
Right. Well, it sounds like this is
Mm.
an important enough design principle that like it's something that you want to design in because it will save costs later in terms of failures, right? That's basically what you're designing in here, it sounds like.
Yeah, exactly. But also just it sort of, fans out into the way that you are managing mission operations, right? So it decreases the difference between running a test campaign and running the mission campaign, right?
Mm,
So that
yeah.
when things are on the bench and you're, running like maybe a fake mission on the bench or something, in many respects, you want that to look as minimally different than the actual mission, right?
Right. Yeah, you don't want to get on the launch pad and be like, "Oh, wow, there's a lot more data now."
Right. Or the other way around, like, "Oh,
Yeah.
I guess I was relying on this data that I was getting over JTAG or, like, my
Yeah,
debug
that's a good
UART."
point. Yeah, yeah. Did we were we not piping that those 4 sensors back to the main control? Because
Right.
that's kind of important.
Right, yeah. So, a lot of these things come down to making the final system operate in the same way that you would be doing test or debug, right, sort of things. So, like, anytime so, like, in the early bring up of your system, you encounter some problem, it might be very tempting to, like, very quickly just sort of throw JTAG on there or, dump some stuff over UART. And, if I was working on a commercial system that's probably fine because, once it's in a plastic shell and on a shelf or whatever, you're way past where you're going to care about debug data. But that's not necessarily the case for something like a launch vehicle or something. Anytime you encounter some error or bug early on, figure out how you can get that data in the sort of data stream that you're already consuming, right?
Yeah. Yeah.
And yeah, it takes a little bit more work, but it pays off in the long run because you get that sort of observability into the system.
When you say so you're saying some people would, in the absence of having all this sensor data kind of out on the main channels, you're saying they would have it as like you're talking about like trace data? Like so you maybe expose trace data instead of plugging in a JTAG? Is that kind of what you're saying, or why did you say a JTAG on there?
I use JTAG as an example in terms of like the richness of the data that you
Uh,
can expose, right?
mhm.
So let's say you have a real-time operating system with a bunch of tasks running. You can instrument when a task was activated, how long it ran, did it like overrun its constraint, its real-time constraint.
Mhm. Yeah,
It's
right.
basically failed a deadline.
Yep.
And you can either emit that as like a constant stream, or you might determine that, well, I don't need to have a stream of every single time this task ran. That might be ridiculous.
Yeah, I
But you
see.
can maybe maintain some statistics on it, right? So minimum runtime, maximum runtime, average runtime, and then like a counter for the number of times you miss the deadline. And that'll help you during your early software implementation and testing campaigns and such. But obviously, the idea is to like make it error free, of course, by the time you're going to run
Sure,
a
yeah.
mission.
Yeah. Okay. All right, so we have no modes. We have debug data and test data is first class data. Were there any others?
There'd be quite a few.
Yeah. Okay.
Some of the like safety slash yeah, let's call it safety. So some of the safety related ones come down to I guess you would call it like the principle of least surprise, right? So there's a few principles that are related to that. So one might be that when you power on a system, it causes no action,
Oh, oh
right?
yeah.
So going back to like that example with like a technician, you've got the vehicle on a, I don't know, maybe it's not a full vehicle, but maybe you have all the systems, or maybe you're testing an engine. You have all the systems like kind of flat out on a bench, or maybe you're actually testing a engine or something like that. You don't want someone hooking up the power and then an actuator moves
Hmm.
or a bunch of valves click, right?
Yeah.
You could either seriously injure someone or cause a fire in the case of, testing a launch, oh, sorry, like a rocket engine, right?
Yeah.
So that's a pretty simple principle, right? So that feeds into like a knowable system, right? So you've just eliminated a whole class of problems.
Yeah. How would you test against that then? Is that just you just power it on a bunch and you say, oh, nothing's happened, or is it more like when you're doing design reviews, it's like, oh, well, this should be a pull down instead of a pull up because of the principle of least surprise.
Yeah, that factors both, or that feeds into the electronics design and the software design, right? So the software can, I mean, it's simpler from maybe a software perspective where you simply don't do anything. Well, I was gonna,
Set everything to zero.
yeah, the next principle I was gonna go into would be like boot up causes no action either, right?
Yeah.
So
Yeah.
simply having the system power on, like the software loads for the first time, like your microcontroller boots up, or you reset the microcontroller, right? Those things OSHA shouldn't cause any action. And the same thing for the electronics. You could maybe say, the electronics have to power on in a known, totally inert state, right? So,
Yeah.
right.
Right. Even if the wrong firmware gets loaded, it's still like there's nothing that's like, oh, well, you better set that output to zero at the early in the code or else.
Exactly. Yeah. So in your design reviews, you're just checking that, like, right, everything is bootstrapped correctly in terms of, right, pull up resistors and that
Yeah.
sort of thing, or outside signals are basically excluded from the system or something. If,
Hmm.
I don't know, dangerous in some way. All of those things sort of feed into another principle, which is, the system is only, the way I like to put it is like the system's only hot under control. So basically, no physical behavior will happen unless there's a control signal.
That makes sense. Yep.
Yeah. So let's say your primary controlling software has come up and issued commands to something, those things do not do things on their own.
Okay. That's great. I mean, some of these things, like these seem kind of like not space specific. These are just good design principles as well, right? These are great. These are great, actually.
A lot of these things developed sort of over the years for different
Hmm.
systems before I kind of got into the new space stuff.
Hmm. I think that's really great because it's then extensible, and like people listening are like, oh yeah, I should be doing that too. Like, this is just a good design review and design principles in general. So that's great.
Yeah, I think they're mostly generalizable. So,
How about the only one that maybe not isn't is like the rocket fire part should go down normally.
right, right, yeah, pointy side up, fire side down.
That's right. Yep.
Yeah, so and then, well, if you're talking about, well, if these things should only have behavior if there's a control signal, then this one's not necessarily a given, but you might want to say, well, there's only a single source of control on the system at a time. So that might be like basically a single process. Only a single process is allowed to emit command signals to your end effectors, right?
Is that tied into like RTOS type stuff? So you start talking about like the mutexes and the semaphores of the world.
Not exactly.
Okay.
It's more This is more related to nodes on a network who's allowed to send
Ah,
commands to each other, right? So multiple you don't want to have multiple systems issuing commands at the same time necessarily.
okay. So this is like a who's in charge here kind of thing.
Yeah, there are systems where maybe you necessarily need to do that, but
Hmm.
generally, like, those are pretty far out there, complicated systems. you can eliminate a lot of complexity and make it, make it a analyzable behavior by simply knowing that only this one system is this one component is the node that can emit like command messages on the network.
Yeah. Okay. Yeah, yeah, from a troubleshooting perspective, I can imagine that's super critical as well, because then it's like, well, the only thing that could make item B do its thing is item A, and so let's go. Item B failed. Let's go look at item A.
Yeah, yeah. Like all these things sort of what they're really doing is like you're limiting the state space that the whole system can be in, right? Like, oh, well, if you have a situation where command and control is being passed around to different nodes, right? That becomes really hard to debug, right? Like you just said, right? Like, oh, it's like combinatorial problem of like based on these set of messages, or each time you run the system, like you might get a different result because based on the timing, a different node was emitting commands at a different time, right? You just kind of can eliminate those
Yeah. Yep.
problems.
Okay, that's great.
Yeah, like another one, all of your communication channels, so whatever that is, like Ethernet or CAN bus or RS-45, like those packets are, let me rephrase that, not packets necessarily, but the messages are globally unique, right? So what that means is if you say have a command message for a particular actuator, let's say if you took that packet and you sent it to any other node on your network, it would have no effect.
Ah, yes. Right.
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 So
Right.
you don't want a situation where if you like say there's an error in the addressing, a particular bit string of information could be misinterpreted by two different systems, right? So like let's say you have two microcontrollers on a bus and one of them is controlling an actuator and one of them like a linear actuator of some sort and one is controlling a valve or a bunch of valves. Let's say you send a message to control this linear actuator, put it in a certain position. You don't want to have a situation where if you sent that same packet accidentally to because the
Yeah.
addressing got messed up or something.
Yeah, like a bit flip, like you were talking about earlier, right? I mean,
Yeah.
that's a worst case
Right.
scenario.
A bit flip or whatever. Or even just configuration error or something like that, right?
Sure. Yep.
Yeah. You don't want that same packet to be interpreted by this other system and have some different effect. You want it to have no effect, right? I mean, the easiest way to do that would be like you have like a message ID in the packet structure, and those message IDs are unique to the physical system, but globally unique, right? Does that make sense?
Yeah. 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 I think so. Yep. Yeah, because you could have like I think what you're trying to I think what you're kind of getting at as well is because you could have like node systems. You could have like a tree where you might have subsystem A, subsystem B, and each of those subsystems has subsystems that might be they each have 5 subnodes on each of those, and you're trying to send a subnode number 1 on tree A, but you send it on tree B, and it still shouldn't work, right?
Right. Yeah.
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 That's the global piece. I can imagine because you'd have like inheritance, all that kind of stuff, but it should still be like there's no way that even if you send it to the wrong neighborhood, that the house address should be so unique it's just not possible to talk to it.
Exactly. Yeah. Yeah, like another kind of follow-on principle for that might be that when you are sending commands to subsystems, you are sending sort of the absolute state that you want that thing to be in, right? So, like fundamentally, like a simple example would be you're not sending a command that toggles something.
Ah, interesting. I thought this was going to be like a calibration type of thing. You're just sending raw values, but you're saying you're not saying switch state. You're saying go off or go on.
Right. Yeah, you don't want to have something that's like, right, toggle this thing from you toggle it, right? So
Right.
in the case that
Right.
you miss a packet or you get the packet twice on accident, you know, or something like that,
Yeah.
you don't want to end up in basically an unknown state.
Yeah, that is an interesting thing. I mean, like, does in these kind of systems too, do you go out and query all the things that might be on a CAN bus on a regular basis as well, or is it more like you have so you have a controller and the controller assumes what the state is of all its subsystems and all the sensors and stuff like that. But then, because of resilience, do you then go and double check it, or how does it really know what the current state is of the stuff on the other end of a bus?
Yeah. Yeah, when you're talking about CAN bus, it's definitely, and there's two ways to approach generally knowing what all the state is, right? Like CAN bus specifically is sort of like, you're just collecting these streams. Sort of the default way you think about CAN bus is like sensor systems are emitting sensor data, and built into the protocol is sort of like a collision detection mechanism. So it's okay that everyone, basically all of your nodes are babbling, basically.
Yeah. Yep.
And the other way of maybe thinking about it is you have a system where no one, or no subsystem is babbling. You have to explicitly send a request for data. And you can do that on CAN bus too. There's
Oh, sorry. Babbling, it would be like emitting packets without waiting to be told, or it's just as soon as there's a opening, it just
sorry, yeah.
starts sending.
Yeah, sorry, that actually is a term like in the literature, is like having a babbling node. But yeah, it just
Oh,
means
okay.
that you have a system that is emitting data without being asked for the data.
Got it. Okay. Yeah, because when I was working in power systems, it was very much like there was like a master controller, and it just said it did not it did not allow you to say. I think you could maybe on the bus you could say like I have data, but that was it. You couldn't like start sending it. It would be like you're kind of like raising your hand, and then the teacher's calling on you and saying, "All right, what's your data?" Like that sort of thing.
Exactly. Yeah. There's a depending on the system you're building, it's not necessarily obvious that like one of these things is better than the other. Right? Like obviously, like I think, you know, a lot of automotive systems sort of use like a common sort of CAN bus method of these things are just streaming, and the priority of the message deals with collisions, and it sort of works itself out. But in the case where you want sort of nearly absolute determinism of the system, so like if you power the system on and you send it the launch the vehicle command, you want everything to be as deterministic as possible, including like, just even the ordering of packets on the network. And that might be that I think that's a little unique in terms of approaches to distributed embedded systems. Like it's kind of,
Yeah.
there are a lot of systems where you don't necessarily need to care that deeply about just how deterministic everything is, right?
Yeah. I mean, I guess if you were getting in your car and just driving down the block, and it had to be the exact same each time,
Right.
then maybe you would be able to do that, right? Because you'd be like, okay, I know what's going to interface here. I know all the things that must go the exact way that we expect it to, because it's so dangerous to drive it up the block. Uh, that's kind of what it comes down to, right?
Exactly. And then it depends a little bit on the makeup of the sensor data you're talking about. Like there might be a lot of sensors, like say on any system like a car or something, where these things are interesting, but they're not mission critical to driving the car, right?
Right.
And something like a launch vehicle, you don't really have a lot of extra nice to have sensors
Yeah.
necessarily. They might all be sort of critically important sensor data.
I'm just imagining someone in the control room being like with like a simulated steering wheel and gas pedal and be like, "All right, guys, I'm gonna floor it. I'm really excited. I really want to see what this system can do. I'm gonna floor it." It's like, nope, it's already floored.
Right, right. Right. So, I mean, like a car system is not going to be designed this way, but like, for example, right, you want your accelerator data to always override like some temperature sensor, right? Or
Yeah. Yep.
your
Yep.
brake pedal position is always overriding whatever, some temperature sensor. And something like a launch vehicle, the likelihood of you having those two radically different priorities is maybe, smaller, right? So like your temperature data might be critically important, right? Your pressure data is definitely critically important if you're talking about like uh rocket engine like chamber pressure or something, right? So it might not you might end up with a system where it doesn't make sense that this has a lower priority, right? You have to get all of the data. And so you're kind of in this situation where you may not be able to use like a sort of standard CAN bus priority way of dealing with your sensor streams. So it might make sense that you just use this sort of request response mechanism for everything where you have some source of control or some controller, whatever your main computer that's requesting all of the data all the time because you need all of it and you need to have it with a real time constraint for every like whatever GNC cycle it might be or whatever it is.
Hmm. Yeah, that's really interesting. So I guess one thing that's kind of missing for me here. So like these are really good general like design. I think, like you're saying, these are all kind of constraints and how you're working the constraints within the system that you're building and stuff like that. But for all of this, where do you start? Because I mean, we were talking about constraints, and that makes
Mm,
sense for this is a differently constrained system. But I, aside from just the what sensors might need to be in there and all the things that are needed,
mm,
like how do you push back in a design meeting and be like, well, no, you can't have 15,000 valves, or you can't, like how do you then start to actually interact with a team that wants more and more sensing because of all these things? I mean, is there like a
mm.
general knowledge around what is needed in a rocket? I guess I'm so clueless in this space that I don't know where to, like you start with a blank sheet of paper, but I'm guessing you don't actually start with a blank sheet of paper.
Well, at Astra we did, but
You did. Oh, okay.
yeah.
That's really interesting. Yeah. So you start with a blank sheet of paper, and then they say, well, a rocket's going to have blank number of valves for the fuel system, right? That's someone said that.
Yeah. Well, so there is sort of like I mean, all engineers want more data all the time, right?
Yeah,
So
exactly. Right. So then what are the constraining elements? Is it cost? Is it time? Is it complexity? Is it weight? I mean, that's one thing I know about rockets is weight matters. So like how do you say, no, that's too many? 8, fine. 9, no, that's too many.
oh, I
Like
see.
I don't know where this comes in, I don't know how I would start that conversation.
Right. So if you're going back to basic principles and those things can kind of flow into like the system that you want to design from an electronics and software perspective. So, okay, based on this behavior that we would like from the system, we're going to use Ethernet and we're going to use this processor. And, of course, like basic stuff like cost and availability are going to go into like which processor you're selecting and
I'm
Ethernet
sure
switches
there's
and that sort of thing,
never
right?
going to be a problem with availability. I mean,
Yeah, right.
right.
No, definitely. Definitely not.
Yeah. Yeah.
So if you're designing like the embedded electronics, right, you'll have some baseline for like, well, I have this much compute power and I have this much network bandwidth. And you do need to like sort of push that. How do I want to say this? The discussion with like the example of like a rocket company with the propulsion engineers and all the stuff they want, right? You can get that information early, but you can't really say yes or no until you've kind of figured out the design space for your own systems a
Yeah.
little bit, right? So you,
Okay.
you have
All right.
to, based on some very probably broad requirements at first, you figure out, okay, well, we're going to use one of these three processors and we're going to use Ethernet. We're going to use one of these three, Ethernet switches or whatever it is. You do need to do a little bit of, you kind of need to create like depending on where you're from, this might be called like a walking skeleton or a vertical
Hmm.
slice, right?
Okay.
So it's what that means is basically instead of developing one subsystem or implementing one subsystem and like finishing it and then moving on, or doing 100% of the design for some system and then implementing it fully and then moving on, like kind of like a waterfall approach.
Yeah.
You do like a walking skeleton, which is just like each, I have a understanding of what this topology is going to look like. There's going to be like this one guidance computer and then a couple different like controllers that are connected to that make things happen on the launch vehicle. So, what is the most basic thing I can get implemented on all of those systems that will show sort of like what this how this system is going to behave, and like get some idea of how much extra compute, or how much, like how many cycles basically you have to play with on the
Mm,
processor. How much bandwidth does it actually take to send one sensor, data, and it could just be a fake sensor hard coded thing, right?
yep.
So
Yep.
you have to
Okay.
have some idea there, right? And you can do these things on paper, right? Like you can just look like, oh, the basic Ethernet packet is 1,500 bytes, and there's this much preamble, and then blah blah blah, and then there's these couple other fields in the Ethernet packet, and then maybe you have a TCP header or UDP header, and that takes up this much space, and then I have this many bytes left over. I can figure out, oh, if I'm sending like a bunch of 32-bit numbers or 64-bit numbers, I know how many sensors I can fit in there. And you
Yeah.
can just do that on paper and then figure out what basically your link budget is. And then you can
Yeah.
come back to your propulsion team or whoever it is and be like, I know you want 200 temperature sensors on here, but that's just not going to happen.
Also, purchasing would like to talk to you.
Exactly.
So I guess even at the level of like knowing that you're going to have Ethernet on there, like that also is a system design that has impacts as well, right?
Exactly. Right. It kind of comes down to sort of kind of hitting the books in terms of like how these things work at a low level, right? So
Mm-hmm.
from a desktop user perspective, you get like an Ethernet switch and you just plug things into it, and you kind of don't care how those packets are flowing around, right? But if you care about sort of like variant, like your jitter and latency, or just wanting to know what they are and what they will
Right.
be, then you sort
Lack
of
of collisions in a TCP system might be might be problematic as well, right?
right. Yeah, I mean, like a modern Ethernet switch does a lot of really smart stuff, so that
Mm-hmm.
chances are you're not going to have a collision or dropped. I mean, it's a switch, so basically
Yeah.
all those different ports coming in have their own queues, and then internal logic is like you know depopulating those queues and sending the packets to the right place, that sort of thing.
Mm-hmm. Yep.
But
Yep.
even just knowing that is important to know, like, well, how do these things find each other? Like, if you're really looking at bytes on the communication channel, right? From a desktop perspective, there's actually a lot of stuff on your communication channel that you don't see, or that's not related to the web page you're viewing or whatever it is. There's all these like lower level protocols to figure out, like, well, which port on the switch is this thing actually connected to? So I send this packet coming in on the right port, right? So kind of just that's like maybe
Yeah.
getting into
Yeah.
the
Yeah.
weeds there, but you want to know.
This all that ties together, though. I think that is what it really to my ears. This is like each decision has cascading effects, right? Each one,
Mm,
you know, deciding to use Ethernet. Okay, well now each board has to have Ethernet, and like, oh, maybe each one has, maybe it's running embedded Linux, or maybe it's running bare metal, or maybe it's running an RTOS, and like just like each of those then also has their own effects, and on down the line to the eventually at some point you have to tell a propulsion engineer, yeah, no, we can't do that. Sorry.
right, right,
And
yeah,
I think one thing it sounds like you're good at is doing that quickly. That sounds like it would be probably, you said you only had 6 months, so probably pretty important to figure that out pretty fast.
yeah. One of the things there is we use, like I think generally speaking, we just use the term requirement pretty loosely, right? Like
Mm-hmm.
everything, some team, like if you have team boundaries, right? Like some team has a set of requirements that they give you for like basically what they want from the system.
Mm-hmm.
But you kind of really need to be really kind of ruthless in terms of what is a requirement
Yeah.
versus, there's other terms for what's the next in line behind requirement. Like sometimes people I've heard desirement.
Oh, I haven't heard that one before. That's a good one.
Yeah, like you have requirements and desirement.
Like a nice to have. I've heard before.
Yeah, but actually, there was a propulsion engineer at Astra who had a really good way of putting this. I don't know if he'd be comfortable me giving his name, but I actually named this after him. I don't know if he even knows it.
Oh, okay, got it.
It's called I call it Judson's razor.
Oh, nice. Instead of Mr. Occam, it's Mr. Judd.
Yeah, Judson's razor. So what this razor is basically a requirement is something that will cause the schedule to slip indefinitely until it is met. If it doesn't meet that
That's
criteria, it's
yeah,
not a requirement, right? So
interesting.
anything else is like a desirement or an objective or a stretch
Could you
goal
state
or
that one more time? So it will cause the schedule to slip indefinitely until it's met. That's a hard requirement. Is that right?
just in general, like that's what a
Hmm.
requirement means, right? Like that
Hmm.
was his way of thinking about it. So if you're going to call something a requirement, that means,
That is the test for it. Yeah.
yeah, that's the test for it being a requirement is that the schedule will just slip indefinitely until the requirement is
Right.
met.
Right. The main fuel valve has to open.
Right. Yeah, exactly.
That is a hard requirement.
Right. Yeah. So going back into that, like sort of back and forth with like how do you
Yeah.
design
Yeah.
these things? There are going to be some requirements like these two valves have to open within 10 milliseconds of each other, which, that might be a little short for fluidics, but whatever it is, right? Like these two things have to happen within 10 milliseconds or something. And you need to be able to do that. So that feeds into like your electronics and software
Yeah.
design.
I mean, you've mentioned meeting timing a couple times. Does this mean there was an RTOS on board?
Yes.
Yeah. Because we had an RTOS expert on here, so basically, I and all of our listeners are all RTOS experts now, because I know what that means.
Oh, yeah. Excellent. Yeah.
It's interesting too because so I work on Zephyr stuff
Yeah.
for some of the networking layer stuff, but it is also an RTOS, and I have no visibility into the actual real time aspect of it. But this is a very good example, it feels like, of the need for that real time aspect. You need to meet timing. You need to make sure those two valves open them within 10 milliseconds of each other, or else you're at least going to send a packet, like you said earlier in the show, that, hey, you missed timing 4 times in the last minute or whatever it is.
Right. Yeah. So that kind of goes into before you start writing any code or designing anything, figure out what class of problems you have, right? So in our example, you have distributed system problems and you have real-time problems. And so, part of that is sort of once you know that you have those problems, it's like those are domains of study and you kind of need to suck it up and hit the books a little bit, right? So what does it mean? Well, first of all, what does it even mean that something is real time, right? So,
Yeah.
like the basic version of that is if you are relying on a result from something, whether that's reading a sensor or a computation, that result has to be available within a certain amount of time or there's a failure, right?
Hmm.
And then you can kind of take that a next step like well there are classes of real-time systems. What is like the classes of real-time constraints? What are those? Well, there's sort of this list varies a little bit, but like generally you're going to have soft real-time constraint, firm real-time constraint, or hard real-time constraint. So a soft real-time constraint might be if that result is late, then the system performance is degraded. A firm real-time constraint would be if a result is late, that result is no longer useful at all, but the system doesn't fail. And then a hard, real-time constraint would be if that result is late, then the system fails.
Hmm.
So once you know you're dealing with a real-time system, it pays to like start by thumbing through some of the literature on these things, grab a book, et cetera, right?
Well, I mean, people listening right now, they're just saying, "Come on, Charles, tell us what is the literature." So what is your go-to on this stuff?
Excuse me while I rotate around and look at my bookshelf.
He's a paper person. He needs to look at the paper.
Yeah,
Understandable.
so I think the two that kind of got me sort of pretty well bootstrapped are two books that are both by they're both published by Springer. One is by Giorgio Battazzo, and the other one's by Herman Kopetz. One is the Kopetz one is real time systems, and the Battazzo one is hard real time computing systems. And I think if you pick up the Kopetz book, like you will have a really solid foundation of what all this stuff means and how they work together. Or not how does what all work together? Like how do how do
The system pieces.
sorry, sorry, I skipped ahead there. Like what does a what does the scheduler do? How are the what are all the different ways a scheduler could work, right?
Got it. So this is
Um,
this is within the processor itself, not at a system level, but at like a board level almost.
yeah, I mean, when we're talking about dealing with tasks that have to do something in a with a real time constraint, these books are like kind of talking about the general principles that go into designing like a real time operating system. And of
Yeah.
course, you probably don't want to bite off developing your own real time system,
No, no,
although
no.
that's
People love doing that.
not. I mean, there's some people who think that's ludicrous. It's not necessarily as out there as it might seem, but you want to
Well, it does for
know.
me, but for some people, I'm sure it's very within grasp. Yeah. Seems like it would be for you.
You want to know like how those things work, and even if you choose a specific real time operating system, there are
Hmm.
probably different tuning parameters or even schedulers and things that you can choose from.
Yeah.
So you might have like in terms of getting your task done, it might be highest priority first, right? So if you have two tasks that try to activate at the same time, the higher priority one wins. Or you could, there's tons of different ways these things work, but it might be earliest deadline first. So whichever task fires up that has the earliest deadline, that gets run first, regardless of right
Uh,
some concept of priority and that
yeah.
sort of thing.
Yeah. Because I guess you don't know the length of time it's going to take to do any one task. So that's probably the best guess you could probably do is just like, well, unless you have like a running list of like, well, this task almost always takes 300 milliseconds, so we need to make sure we allot that, and that's what schedulers are for, right? Well, not
Yeah, and well,
exclusively.
that kind of ties back to sort of the those guiding principles that are sort of around like having a really well testable system and a knowable
Hmm.
system, and sort of like test data is first class data, right? So the first time you run this through, you can get if you have like these synthetic software sensors coming in your telemetry stream, you can just run it once and know like absolutely like, oh, to send this one command to this actuator two systems down, I know that it took so many milliseconds on the network to get there. Then it took so many more milliseconds for that system to parse the command, execute the command, and respond. Right, like you can get all that instrumentation and then just
Hmm.
know how long these things take, and then feed that into your sort of analysis of, okay, well, I know this takes 300 milliseconds to run, and I know this
Hmm.
has to run within 350 milliseconds or whatever it is, like, and these other things kind of stack up. How do I structure the schedule such that all these things actually occur?
Yeah. Thread the needle, as it were. Yeah, it's interesting. I mean, so when you say, so you have a real time operating system, you have this device that's maybe, so we've already learned that there's a Ethernet going to a end point of some sort.
Mhm.
Is that kind of the final stop, or are there then subsystems? So like a, I'm just going to, I have literally no knowledge of what these boards are, just to make sure that we're not, giving away any secrets here. But like, if I'm just imagining like some like LPC 5500 part or something like that, some
Mhm.
like, relatively beefy microcontroller running an RTOS. And then I had said earlier, like, well, it's not really there's not like a system view, but it's just a microcontroller view. But then I was thinking, well, maybe you could though, because you could have additional microcontrollers down the line that are maybe on the other side of a SPI bus or an I2C, where you actually control sub microcontrollers as well that are just sitting on an actuator, just measuring position and just feeding it back to the real-time operating system. Like, what is the depth? Like, is it the real-time operating system is that final stop in
Mm.
the system design, or are there sub stops past the real-time operating system as well?
So, yeah, a real-time system, like adding a real-time operating system. How do I say this? Like, a lot of stuff comes with a real-time operating system that seems sort of like, oh, this is just obviously good. I have these events, like generally speaking, I have, some event-driven system, and button pushes, have a certain priority, and updating the screen as a certain priority, etc. And I just want to make sure that the screen always updates, and I, don't care necessarily when the button push is registered, because on a human timescale that doesn't matter,
Yeah,
right?
right. Right, 30 milliseconds or 200 milliseconds, yeah, who cares?
Yeah. So the threshold for using a real time operating system is a little different, right? Like depending on what kind of system you're dealing with.
Hmm.
So it doesn't come for free, right? So there is sort of like, some complexity with structuring your code for a real-time operating system and knowing how the real-time operating system is going to execute that code. Going back to the like kind of guiding principles, right? You're trying to keep the state space as much as you can into something that's like kind of knowable by, in best case scenario, one human, but at least like the team, right, can like know
Yeah.
what's going on. And so if you kind of approach it from that perspective, then the threshold for adding like something like a real-time operating system might be much higher, right? So and the number of like legs in, like you were talking about, like the number of legs, like how far away you are from the center, the main
Yeah.
computer, and
The
like the thing
brain, yeah.
the
Yeah.
brain and the brain and like the fingertip, right? Like how many
Yeah.
different things are in that
Yeah, that's a
path.
good way to visualize it. Yep. Yeah.
Yeah, same thing, right? You want to limit the amount of stuff that happens between, right, the brain and that.
Yeah, the brain says wiggle finger. How many hops does it take to get down to finger? Right. It's just
Right. Yeah.
so
And so right.
so I specifically in a rocket, I guess, or maybe a
Mm.
small. Let's just say this rocket. How many steps is it to get to the finger waggle?
Right. Yeah. So I mean, that's not talking about like any specific
Yeah.
rocket,
Yeah.
but generally you want to just limit that to like one major like
Oh,
network hop.
okay.
Yeah.
That's
So
great. Okay, yeah, that's what I was wondering. Yeah, so then you're saying, so I'm just going to extrapolate, so you're not saying anything that you shouldn't be saying, but like I'm just imagining an actuator in like the real time. So this LPC whatever microcontroller running a real time operating system is directly reading and writing to an actuator instead of writing to a over a bus to a sub microcontroller that is then updating that actuator. Is that a fair statement?
that is a fair statement. Yeah. So
Yeah. Okay.
so like the performance of like say a spy bus, like
Hmm.
between your microcontroller and an ADC or something, like that is a really it's pretty easy to understand what that's going to look like from just looking at the data
Hmm.
sheet, right? Like, oh, I
Yeah.
can run the
Yeah.
spy bus at this speed, and basically I just know that I can get all of the data off that spy bus. You can kind of, at some level, you can assume that's basically like a local interaction, and you're not
Yeah.
like, it's not like a net. I mean, even though, sure, it's a communication bus, you don't have to factor that in exactly in the same way as like your primary
Yeah.
communication bus, right? So you can kind of just think of like this subsystem, which is a microcontroller, an ADC, and like I don't know, a bunch of like high side switches and stuff like that,
Mm-hmm. Yeah.
right? You can just think of that as like the a single like sort of domain of control,
Yeah. Yeah, that is a subsystem, right?
right?
That makes a lot of sense to me. What this really tells me, though, is that when the complexity goes up, so now the propulsion engineer comes back to you and says, Charles, I don't need 8 actuators, I need 16. It's not like if you run out of IO or drivers or whatever is on these control boards on the RTOS based control board, it's not like, well, we're going to try and move this down the line and put sub processors off this real time operating system. It's no, no, no. We just duplicate that board and we say, all right, now there's just a second node on the network that
Exactly.
has a
Yeah.
similar functionality. And that actually then, from a standardization perspective, that makes a ton of sense to me. From a, unique devices on an Ethernet network, that makes a lot of sense too, because then they're very easily addressable. So like, yeah,
Yeah. I mean, you're changing the problem from like you add another spoke to a hub and spoke
that's right. Yeah.
topology versus like if you have a tree, you have to like potentially rebalance this tree because of
Yeah.
bandwidth constraints. And it also just makes it harder to visualize like what's
Hmm.
going on.
Yeah. Yeah. So then how do you then handle when you have, so assuming you have standardized hardware where there's the hub and spoke and you go from 2 spokes to 5 spokes or something like that,
Mm.
but each of those spokes, each of those real-time operating systems might have a completely different function even if it's similar hardware. How do you then maintain all of the updates that need to happen from the computer going down to each RTOS based system?
Right. So some of that, well, first I would say is maybe those sort of nodes on the periphery,
Hmm.
the actual end effectors, the end nodes, those don't
Hmm.
necessarily need to run a real-time operating system.
Oh, okay. But then there's more complexity, I would imagine, as well, is because then if you have a real time operating system based version and a non real time operating based version, you're saying they're all on the Ethernet network, but they're
Oh yeah, I certainly I wouldn't recommend necessarily mixing and matching these things,
yeah, yeah, yeah.
but if you have like a situation where the end nodes don't make decisions for themselves necessarily, like high level like system behavior decisions, they might have like a little
Hmm.
small like they might be running PID loops or something like that, PID
Yeah, right.
controllers or something,
Yep,
but
yep.
they're not making large system decisions. They're only sort of waiting for a request on the network and then responding. That might be a interaction that you don't need to necessarily have a real-time operating system.
Oh, that's great. Okay.
In that case, it can make it quite a bit more knowable, right? There's a lot of different stuff you can do between just having a state machine and a real-time operating system, right?
Yeah. Yeah. Yes. Yeah.
So you can kind of almost fake, not fake, but like there's some sort of basic like real-time operating system like behavior that you can get without having to run like a
Yeah.
task switching system,
Hmm.
right? Like a simple version might just be like you have a standard super loop, and when events come in, you're setting flags, and then you just check those flags in the priority order that you want to get them
Hmm.
done, right?
Yep.
Or
Yep.
you respond to them, or you add them to a queue, and then you just
Right.
respond to them.
And then you're saying because your system has so much overhead in that scenario that you're not even worrying about timing. It's just like not a guaranteed, but it's you're not as worried about timing and deterministic type stuff then.
Yeah. Well, I mean, and you're so close because you don't have the operating system in the way. It's
Yeah, right.
actually, in some ways, a little bit more knowable and a little bit more real time, right? Or not more real time, but the latency is going to be
Yeah.
smaller because
It's
you don't have this operating system like
zippier. It's zippier.
yeah you're not like switching out the context for one task and storing that
Yeah.
while you
Yeah.
load up the new context and like switch over to a different stack and start executing something.
Hmm. Okay. Well, did the rocket go up?
Yeah.
What was the timeline of this? Like when were you there and when did it go up?
Oh, I see. I joined in the middle of 2017, and the first vehicle launch was 364 days after I joined.
Really? That's a nice stat to have.
Yeah, so it was like 1 day short of Todd and I's 1 year anniversary.
You should tell people that the deadline was the 1 year. They said we
Yeah.
had to get it out in 1 year.
I mean, yeah, actually originally, like I said, when I originally joined, it was the idea was 6 months, but that's
Yeah.
was just not feasible for
Yeah.
the size of team we had at the time.
So you're saying complete blank sheet of paper on day one. No electronics design. Maybe some rocket part design. I don't know how. I don't know how
Mm,
propulsion engineers work.
well, no, so the 1 year is from my perspective. So
Okay.
coming in with the understanding that I was writing from scratch the flight control software, that was a year.
Ah, I see. Okay.
There was already heritage in terms of the actual rocket engines, and there was actually already
Cool.
some heritage in terms of the electronics.
Got it. Okay. So like so some rework maybe or just but yeah, okay. So blank page for you. I get it.
Yeah.
Cool. That's I mean that's impressive either way. Don't get me wrong. And so like so what is the scale of how much can this thing take up in terms of like how many small sats can it carry or weight, I guess?
So, well, it depends on, yeah, it depends. So there's like, you've heard of the term CubeSat potentially.
Mhm. Yeah.
That is actually a form factor. So a
Mhm.
CubeSat is basically a 10 by 10 by 10 centimeter
Yeah.
unit. A CubeSat might just be that one unit, or you might have a 3 by 1, or there's different configurations of these things.
Yeah, 30 by 10 by 10. Yeah, well I think the
Yeah.
planet one was 30 by 10 by 10, wasn't it?
Yeah, I think that's a 3 by 1. Yeah,
Mhm.
or 30 by 10, yeah. Sorry, so there's some amount of volume constraint, but because CubeSats are pretty small, it's
Mhm.
any launch to orbit, you're really talking about mass is the thing you care about.
Got it.
So I think generally the small launch services are looking at hundreds of kilograms to orbit.
Mhm.
The big guys are
Mm.
launching many, many, many tons.
The SpaceX's of the world and such. Yeah.
Yeah.
Yeah. Oh yeah, I guess I could have gone to the Astra homepage. 500 kilograms to 500 kilometers. It says up to 500 kilograms to 500 kilometers.
Yeah.
Okay,
Yeah. So those orbits, I think, are generally like the small launcher or new space kind of folks are
cool.
in the 400 to 600 kilometer orbit range generally.
Yeah, I don't really get the difference. I know that the James Webb Space Telescope is at the L2. I think it's at an L point. I know that a Lagrange point. Is that right?
Yeah,
L2.
it's orbiting a Lagrange point.
Oh, that's right. That's not. It's not at the Lagrange point. Yes, that's.
Yeah, it's not at the, well,
It's
I mean,
nearby though. I know that, and it's very far away compared to. It's like way past the moon, right? Because the moon is shading it, or the Earth's shading the sun, or something like that.
yeah. So it is. Yeah, it's quite a ways out. I don't know exactly how far that one is out. The idea is to basically keep it oriented away from the sun and more or less in the shade.
Yeah. Okay, so we're already pretty deep on time wise here, but I would
Yeah.
like to know, because we talked about rigor and how does this then? So coming out of this experience and going back into the consulting world,
Mhm.
do you have to turn down contracts because they're like, we just need something really quick, and you'd be like, well, like, do you get asked for fast and dirty engineering, and you're like, it doesn't, that's not my thing, or like, what is your area of focus now that you're back in the consulting world?
Yeah, now that I'm consulting, I do get a few like new space contracts. So like I don't really have to dial that down exactly. In terms of like commercial projects that I work on, I think that's like, kind of like one of the values I add is kind of bringing some of that over in terms of I get a lot of like startups, right? So
In the Bay Area, this is shocking.
right. So they're introducing some new product and they maybe have not done that before, or they don't really know how far away their prototype is from like being able to
Ah,
go into
yeah,
manufacturing. And
yep.
so those skills sort of transfer over in terms of, like actually doing design reviews for them. and also kind of factors flows into general processes that they might be using for their development life cycles. Like a
Yeah.
lot of this stuff gets a lot of this like rigor, gets kind of a bad rap because of like this focus on agile methodologies, especially here in Silicon Valley. Like it's
Mm.
just like this constant word that's flowing around, agile, agile, et cetera. And the worst thing you could ever do is like waterfall, et cetera. I think even waterfall, but in general, like this sort of like more rigorous approaches actually make you go faster.
Yeah. It's slower at the beginning, right? I think then
That's the
there's a
thing.
crossover at some point because you like, okay, I think about this when like Philip Johnston was on the show too, and it's like Philip talks about like, oh, getting set up. It's like, yeah, it's just it sucks at the beginning, but once you're there, then you're so fast because your build system just tests everything for you, or like you're talking about, like all of your systems test every time they start up, or they, all of your data is just there. It's not like you have to go and do things manually each time. I don't know. There's a lot of ways to do it, but
Exactly. So it's yeah, like we're going back to that example of the your test data is first class data. Like the first time you encounter a bug, it's super tempting to just throw, your UART to USB adapter on there and print out some stuff on your UART or hook up
mm-hmm.
JTAG or whatever it is. Like that's certainly easier than like, okay, I'm going to revise the software so that I can actually get that
Yeah.
stuff that I'm looking at.
Let's change our communication standards so that we can have better visibility into what went wrong. It's like, oh yeah, okay.
Exactly. Like that there's more friction there, but in the long run, I think like those kinds of trade-offs just like
Yeah.
really pay off.
Yeah, I think it would be a harder pitch. First off, I think people coming to you probably already know this based on your reputation, so that's good, and hopefully this show will help to and continue to enhance that. But like, I can imagine that would be a hard pill to swallow when people are like, "Well, I want to go fast, though." It's like, all right, well, no.
Right. Yeah. I mean, I see this a lot in the electronics design for like the first like revision of a board. Like so
Yeah,
someone's going from I have a couple like a couple Raspberry Pis or like
yeah.
Arduinos hooked up. That first transition to like, okay, we're going to design a custom board and we want to be able to manufacture this thing. I see this a lot where the pressure is so high to get that out quickly that like these boards just have like no testability, right? Like there's no test points on the things, right? Like all of that. And
hmm
there's no way
Yeah,
to like basically like if the system doesn't just boot up and work flawlessly the first time, like you have no idea why,
yeah.
right?
Yep, yep.
And
Totally.
so yeah, it takes a lot more time to like think about like which test points you need to bring out and you're fanning out a BGA and that's a pain and you know it would be a lot quicker if I just didn't fan out this other communication channel for testing and debugging or whatever. And
Yeah.
it always comes back to make these things actually take longer than they would have if they just slowed down and paid someone to do a design review, get a third party design review, or if you have if you have enough people on your team, make design review a thing and sit down and do the process of like, okay, well, once this comes in and it doesn't work, how do we test it? Right.
Right. Yeah. Having a test plan is pretty important, right?
Yeah.
Yeah. It's interesting too because there, the thing that I've learned in my consulting career is that
Hmm.
there are no guardrails. Like
Right.
one of the
Yeah.
things that like companies give you is someone there who's like, yeah, we've done it this way, and yeah, it sucks maybe, but there's guardrails because that's just how we do things, and like I bemoan that's maybe slower, older process when I was there, but I didn't realize that then nobody was going to be asking me for that. Like when someone's just like, Chris, I need you to design a thing for me.
Mhm.
it's up to me. Like that's on me. Oh, everything that works, everything that doesn't. It's
Right.
yeah, that's all me. And if I then have to say, well, yeah, sorry, I didn't hook up the ground plane or something like that, or whatever other stupid thing maybe I've done, like it's just that it's all on me. Every check is on me, and yeah. So
Yeah.
that's why I like the rigor part. That's where the rigor really is important. I think it allows you to deliver a really good product as a consultant. I think.
Yeah, I agree. So, right, like kind of it's like no process is definitely not the way to go. Like that does not make it faster. You have to have some process. Like there's some terms for this, like the right amount of paper, the right amount of paperwork, right? Like
Mm,
you
yeah.
need to have some process in place for like, okay, I finished doing the schematic. What happens next? Oh, I just do layout and then I send it to the PCB house. No,
Yeah.
like there has to be a couple other steps in there, like check the schematic, like whatever.
Yeah.
Come up with a checklist of things that you always test for these. You always check your schematic against. Then move on to the layout, right? And then have a checklist or something for things that you always check on a PCB, right? Like,
Yeah. I'm just stuck. I'm sitting here thinking about talking to my 20-year-old self and be like, Chris, one day in your late 30s, you're going to be on a podcast, nodding along vigorously to the right amount of paperwork.
totally, right? Yeah,
But like I do, like I am nodding vigorously. Like yes, of course there is. Yeah, it's just what was the other one? I think it was. Oh, the other day. This is a really stupid example, but it is born from years of experience. I was replugging in I was just changing out some plugs on my camera. Like I was just
mm,
redoing my camera. And for some reason, I like kind of like snapped to and I realized I was moving all the glasses of like the last dregs of coffee in coffee mugs and like cans of bubbly water and water bottles. I moved all those to another bench. I had completely cleared them off the bench and I'm like, this was such a good move. And I'm like, how did I learn this? I'm like, I've learned this because I've spilled coffee on every single schematic I've ever had on my bench ever before. And like, and like, but like that slow, slight movement at the beginning saved all the paper on my desk, like, or all the
right,
stuff on my
exactly.
desk, really.
Yeah,
It's
yeah,
just, yeah. Very,
yeah,
very stupid version of all the very smart things you're saying here. So.
yeah. Well, uh, well, thank you for saying so. But yeah, like the it's like a when you encounter those things, I don't want to like go off on like a checklist thing, but like, yeah, put it on the
Yeah,
checklist, right?
checklist. Yeah, that's good. Yeah. I still refer to Andrew Zonenberg's. He's got one on GitHub that I will link in here.
Oh,
Do
okay, great. Yeah, yeah.
you have one published somewhere?
I used to. I probably need to brush it up.
Yeah.
Maybe. Yeah, I could find
You
a
know, the
link to
hard
it.
part about a checklist is there's nothing that forces you to check the checklist.
Yeah, that's true.
that
Yeah.
that first step of like, oh, someone has to make me go through the checklist. That's all on me. If I skip the checklist, it doesn't matter.
Right. Like, can I actually fasten this board to something? Does it have fastening
Yeah.
holes?
Yeah, that's a good one. Yep.
Clear, like connector clearance is another one, right? Like,
Oh yeah.
or like, not. I mean, there's hundreds of these things, of course, but like
Oh, of course. Yeah.
the one that I screwed up a lot before I put it on the checklist was like failing to in my footprints to like draw the mating half of the connector's
Mm.
size, like the footprint,
Yeah.
like the keep out for the mating half.
Yep.
So I'd have this
Yep.
connector
Yep.
that I couldn't connect the cable to because the right connector doesn't fit between the
Right.
other things.
That's a good one.
And just one other thing on the testing too. I think a lot of people fail to account for what happens if the test fails. Like
Mm.
if the test fails or this test campaign fails, you know, how does that affect the schedule, etc. There's a lot of, oh, well, obviously we're going to test, but then there's not a lot of thinking about, well, what happens if that test actually fails, right?
These little tests are big tests. Like,
Let's say design level tests, right? So you get your first board in and
ah,
you schedule in testing because, okay, we have this much time to design the board. We want it out by the end of this quarter, et cetera, et cetera. We have to fit testing in there, et cetera, et cetera. But then there's usually this missing step of, okay, well, we did the testing, but what happens if that board, what if the board doesn't work? Right.
Yeah. Yep. Yeah. Gotta budget for that second rev.
Exactly.
Nobody likes to tell the client that one. That's why doesn't it work on the first rev? Because reasons, man. Just because reasons.
Yeah. And I mean, yeah, you can make a lot of jokes about it in one way or the other, but the thing I find is you are pretty much not going to go from your Arduinos that are like, breadboarded together to like your first
Mhm.
rev, right?
Yeah. Yep.
Even if you get the circuit right, the box that it fits into, et cetera, like it's going to change.
Mm-hmm. Yep. Totally. I mean, is so this rigor checklist, all this stuff. I mean, it sounds like I always hate like talking to younger engineers because they're like, well, what do I go read? I asked you about books and stuff like that too, but the rigor and the checks and the checklists and things like that, are there resources out there for that sort of thing, or is it just School of Hard Knocks?
Mm, I mean, some things you certainly learn the hard way.
Yep.
I don't know if there's necessarily, I mean, there's definitely like a domain of expertise, which is like testing industrial systems and testing, safety systems and things like that. But in terms of electronics design and software design, I mean, I think it kind of comes down to the part that's hard is figuring out, is this problem I'm having a domain of expertise? Like, is this actually, like, does this problem I have, does it have a name? Is there like a bunch
Mm,
of people that actually study this class of problem?
I see.
Right.
Got it.
And like
Right. Right. Right.
figuring out what those things are and reading through, finding some good books on the subject, like that can definitely save you a lot of headache. Like just knowing
Yeah.
like what the problems actually are. Like, sorry, we were talking about distributed systems. Like, what actually are all of the problems with a distributed system? What are
Mm-hmm.
all the problems with like a real time system? Like, even if you're not like, studying all the white papers that ever come out and like publishing, like at least knowing what all of the problems that exist are, right? That'll, I
Yeah.
think, help guide your thinking.
It's like Schadenfreude for other people's problems, right? Like you're like
Right.
going and reading case studies and being like, "Oh yeah, that sucks. I don't want to do
Yeah.
that." You're still gonna probably mess it up at some point. Like that's how I do it. I'm like, "Oh yeah, I would never do that," and then I go and do it the next week or something like that. I'm just imagining myself reading a case study of someone spilling coffee all over their schematics over and over again
Yeah,
and
maybe
doing
that
it.
maybe that ties in with like the right amount of paperwork. It's like finding
Uh-huh.
the right amount of studying, right? Like
Yeah.
you
Yeah.
could take the total agile approach of like, I don't even know what my system's going to look like. I'm just going to start writing code and then
Mhm.
bounce off the edges until I get there. You can certainly do that, but chances are that actually will be you'll learn a lot, but it'll be a painful and in my experience actually slower process than finding a couple good papers and books to read on the subject first.
Yeah.
Mm.
Yeah, like well-designed systems have patterns, and usually for a reason. Usually, either
Yeah,
historical or like theoretical, and like, all right, yeah, maybe like
exactly.
start there instead of just being like, well, let's start with a single processor and see when it fails, and then go to two processors or whatever the equivalent would be. I don't even know, but yeah,
Right, yeah.
I think it is just in certain spaces where they're aside from just like finding a very very similar thing and copying it, which is valid enough if it's not violating patents or whatever. If it's just copying a methodology, that's fine. Maybe it's a simple
Mm.
enough problem. But like I think about like if I was presented with a blank sheet of paper like you were, and I would be very dismayed.
Yeah. So, right. Well, I mean, it can certainly, I mean, it's certainly challenging, but, it can be fun, right? Because it's sort
Oh
of
yeah, I mean you made a thing that you were on a team that made a thing that went to space. That's cool as hell, man. Like that's
it did
yeah,
eventually go to
yeah,
space, yeah,
yeah.
yeah.
That's really cool. I have never done that, and likely never will. So like that is yeah.
Oh, never say never. I mean, I think you mentioned Sean from Planet, or he was at
Mm-hmm.
Planet maybe when you interviewed him.
Yep, that's right.
I mean, that's how I was doing sort of like industrial, commercial electronics and software for just a little bit before I think I heard Sean on a podcast mention that he was working for this cool startup and they're in Alameda. And I'm like, oh, I'm close to Alameda. And at the end of the podcast, he's like, hey, if you think you're interested, like hit me
Oh
up.
yeah.
And I sent an email, and that's how I ended up in New Space. So
Huh. Well, there you go.
never say never, right?
Yeah. Well.
It's sort of
Okay.
like it's you don't have to have a degree in aerospace engineering for sure to get into New Space, but just take it seriously and take studying seriously, and
Yeah.
it can happen.
Yeah, I'd say the stakes are higher than the stuff I'm normally doing, but not unobtainably higher apparently. So that's good.
Yeah, it's not like you can. Yeah, rigorous testing will certainly catch all of your like lack of conceptual knowledge, right? And
Yeah. Yeah.
help you correct for it. Like, oh, there's this edge case. I didn't know about this edge case, but I caught it in testing. Right.
but my test does.
Right. Exactly.
That's great. Charles, where can people find out more about you and how to hire you as a consultant and your background? Where do you hang out?
So yeah, if you want to hire me as a consultant, or otherwise just talk to me about reviewing things, or just talk to me, I have a small presence at grizzlypeak.io. My sort of freelance name is Grizzly Peak Systems. I'm available, like, I think I'm on LinkedIn. I check that every so often in terms of professional, interactions. That's probably about it.
Great. Well, I'll drop a hint if people join the consulting forum as consultants. You also might get to cross paths with Charles too. So
Oh,
that's
sure.
that's
Yeah.
been good for me. Yeah,
It's a great forum. There's a lot of
thanks.
really great people on that forum.
Yeah, there's a very long running thread about part shortages.
That might be, I don't know, but is that maybe the longest one at this point?
I think so. Yeah,
I know.
it's been rough,
My
folks.
my kingdom for some FPGAs.
Yeah. Yeah. Oh yeah. All right. Well, thanks, Charles. I appreciate it. This has been really interesting, and I'm looking forward to talking to you again soon.
Great. Thanks for having me. Cheers.